Good afternoon and welcome to the ESAB Specialty Alloys live event. My name is Clemente Talarico and with me as the presenter we have Mr. Peter Stones. Mr. Paolo Turchiana, Global Product Manager Strip and Wire, as well Mr. Per-Åke Björnstedt, Global Product Manager MIG TIC, are present as well for technical support. I'm pleased to announce here the 10th presentation of ESAB Specialty Alloys, which will happen every third Friday of the month at 14:30 European time via Team Live event. The 10th presentation of the program will be the one starting in few seconds with the title Strip Overlay Cladding, Submerged Welding and Electroslide Welding. What is the difference? We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box you will find on the top right of your screen. We intend to present on about 30 minutes and take 10 to 15 minutes more for answering your questions. So, and now let us start the show with Peter presenting. Enjoy.
Thank you, Clemente. Good afternoon, everyone. Thank you for joining us, getting so close to the holiday time. As Clemente mentioned, please feel free to ask questions via the Q&A box, and we'll do our best to answer them immediately after I finish presenting. But we will have all our contact details on the last slide, mobile phones and emails, so you're perfectly welcome to get in touch with any of us should you think of anything that you've not asked today. Additionally, I always like to say you don't need to take notes of anything. We're more than happy to provide copies of the slides. Again, just drop us an email or a text and we're more than happy to send you a copy. So what I want to talk about today is strip overlay cladding. It's not so much an agenda, but these are the key points that I'm going to cover today in about the next 30 minutes. So why do people overlay weld? Why do people clad? What's the purpose of it? Why go to the trouble of welding? Specifically for strip electrodes, this is what we're talking about today. There are two different processes. One's submerged arc welding, which people are probably familiar with from wire, but also this thing called electroslag welding. So what is it and what are the differences between the two? Obviously, it's critical to what you can overlay is dependent upon the available grades. So what grades are available? Dilution, as with any overlay, dilution is an issue. You're trying to achieve a chemistry on the surface for some purpose. If that gets diluted, then what can you do about that? What happens? And really, the big thing about strip overlay is what deposition rate can be achieved. So, making a start, introduction to weld overlay using strips. So why do people overlay in the first place? And it's really because it would be too expensive to make a solid part or a whole item from the corrosion resistant material or the wear resistant material. It's very much cheaper to get the mechanical properties of carbon steel, high tensile, whatever, of carbon steel, a cheaper steel, and then coat the surfaces that need the protective coating on them. So you can see the photograph on the right hand side there. This is the inside of a vessel, some kind of vessel, and the strip cladding's been put onto the inside. So you've got the mechanical strength from the carbon steel, and all the issues regarding fabrication are in carbon steel. So a little bit easier than stainlesses, for example. Plus, it's a lot cheaper. That's why people do it. Compound plates is another alternative. You can actually buy pre-clad plates and use that for fabrication. But again, that's another expense. Do you need different properties on the inside or the outside of a vessel or a pipe or a plate? So you could put two different coatings on, for example. Basically, you just can't buy. You can't buy what you're looking for. It's not available on the market. The only option really is to fabricate in carbon steel and find some way of cladding it. It's economy. People are trying to save money. That's why they do it. So, in terms of strip overlay, this is just a quick illustration of why go to the trouble of doing this strip overlay. So down at this bottom end here is deposition rate, so kilograms per hour. So with your little TIG rods, manual TIG, then the maximum that you can get down really is about 2 kilograms an hour, and that would take some doing. So no, you wouldn't really do a manual TIG as an overlay for anything large. Moving up to say MIG welding, SMAW, then yeah, you can achieve 15, 16 kilograms an hour. Then when you start moving on to submerged arc, sorry, that's MIG, I beg your pardon, up to 8 kilograms an hour. Submerged arc wire is up to around about 18, and that leaps enormously up to 30 when you're talking about submerged arc welded strip. But the biggie here, as you can see, is this electroslag welded strip. So deposition rates up to 50 kilos an hour. So it's a world away from down at this bottom end. But the other thing to notice here is the amount of power needed. So obviously for manual TIG or for MIG welding, you're well under 300 amps, for example. Whereas if you're doing the big deposition at the high speed with strip electroslag, then you need a device that can deliver 2,500 amps. That's the kind of thing you're talking about. So it may be restrictive for some people if you just don't have that equipment. So talking in detail now about submerged arc welding of strip, then this cross section, it could really look like wire. So we've got wire being fed towards the workpiece. This is the direction, so the welding head is moving in this direction, left to right, and it's like a MIG process. So the actual electrode is the filler metal. So the arc is generated between the base and the filler metal, and in this case it just happens that the filler metal is a strip. So rather than just being a wire, it's a strip. It's submerged arc. So we have a flux. Flux is completely enveloping the arc. It needs to completely envelop the arc. The purpose of the flux, there's numerous things that fluxes do, and one of the main things really is to keep the oxygen out. Keep the oxygen out from the arc. The molten slag, the arc makes the slag molten, and that covers the arc. Basically, so we get a melting away of the filler metal strip, and it's being fed further in towards the workpiece. Very, very similar to MIG. It's the same process as a MIG welding, if you like, in that respect, but we've got it covered by an arc. So in real life, this is what it looks like. So essentially, instead of a coil of wire, you have a coil of strip. Typically, the strips are 0.5 millimeters thick, all of them, and the most common widths that are used are between 30 and 90 millimeters wide. These are available. The most common size is really a 25 kilo because it's manageable by hand, but obviously if you're using thicker strips, then you want more than 25 kilos on it, so you need some kind of lifting device to enable you to use it. So the strip's being fed into the head. So this is the welding head, so that's got the current running through it. For the bigger machines, these jaws will be water cooled. So these are the electrodes, the strip's being fed through it, and you can see the pipes here feed from the hopper, the flux hopper. So the flux is just dropped by gravity in front and behind of the strip as it travels. Now, what's the difference between that and electroslag welding? Well, on the face of it, it looks very, very similar. And the biggest difference that you can see immediately is that the flux is just being fed one side. So the direction of travel is again left to right. And you see that the flux is only put on one side, is only put in front of the direction of travel. The big difference with this is that the flux is actually, it's an electrically conductive flux. Because of the minerals that it's got in it, it makes it electrically conductive. So there is no arc. It's not an arc that is wearing away the filler metal as it's being fed. The it's an ohmic resistance, so very similar to a light bulb. You've just got a resistance between the two. The flux is carrying the current, and the ohmic resistance, because there's so much power in there, makes it molten. And the molten pool, I beg your pardon, the molten pool melts the filler metal as it's being fed in, and it melts the surface of the base metal. So the heating, the melting, is not done by an arc. That's the big difference. It's an electroslag process. So you've got an electrically conductive slag. The process works in the same ways that the filler metal is fed into the molten pool, but it's not an arc. That's the big difference. It's ohmic resistance. So both of the processes use the same strip. Whether you're using the submerged arc welding or electroslag welding, both of them use the same strip. So the strip is not different for the two processes. What is different, as I've mentioned, is the flux. It's a different flux for electroslag welding in that it needs to be electrically conductive. With any flux, the usually you can buy any number of different grades of flux, and it's important to pick one that enables the slag to form on the surface and to detach. What you don't want to have to do is to be grinding the surface of your weld to remove the slag. There's a number of things that fluxes can do and that we can incorporate into the processes, and that could be the whole topic of another conversation. But it's important that you pick the correct flux. With electroslag welding, then you have the possibility of getting high-speed fluxes. So for the highest deposition rates, and I'll illustrate some figures later on, then it's a different flux again. It's a slightly different mix that's developed specifically for running at high speed. Again, we've got the deposition rates in a little more detail. So submerged arc up to about 1200 amps, and then electroslag up to 2500. That's the kind of where we're talking about. So at these kind of rates, you would need a high-speed flux, and obviously a machine that delivers 2500 amps. I've got a little video now that I can show you, so if you've not seen this process before. So this is electroslag welding. It's done in the laboratory in ESAB. So it's not a professional video, but it does illustrate what we're trying to show fairly well. So you see that the flux has just been fed onto the front side of the strip. You see the size of the weld pool. Now you can imagine if you're going wider, even wider, twice the width of this, 120 mil, 150 mil, then the weld pool is enormous. Okay. There is no arc. Yeah, it's obviously getting very, very hot, but there is no arc. You can also notice that the flux that has been fused, if it's fused, then it'll start to form a slag on the surface of the deposit. And then you've got these unused patches of flux around the edges. So these can be reused. It's common practice to vacuum these up, sieve them, and use them again. Okay. If I can go on to the... Sorry. There we go. You see, that's running at 25 centimeters a minute. So 250 millimeters per minute, 23.8 volts, and 1254 amps. So it's in the middle somewhere. Okay. The other thing to notice is with this, when we're getting towards the end, you can see the slag detaching of its own accord. So as it's cooling down, it's starting to lit. So that's a very, very, very good sign. Okay. Mentioned the very, very big weld pool. You see it's still molten way back here with very little fume. So that's obviously a factor of the cleanliness of the metal as well as the design of the flux. So one thing that's very, very important with any overlay is dilution. You have to take dilution into account. You've got an arc welding process, so by definition you're actually melting the surface of the base metal. Now with an overlay, you're not just trying to achieve a weld. It needs to stick, of course, but what you're trying to do is get a chemistry on the surface. That's the purpose of doing a corrosion resistant overlay. With dilution, it means that you've got a mixture of the filler metal mixed with the composition of the base metal, and percentage dilution. It's worked out by an equation. And the big difference is between the two processes that with submerged arc welding, then it's not uncommon to get dilution up to 30%. So 30% of the filler that you've put on top, you're trying to achieve, say, a 625, a nickel chrome moly 3 overlay on the surface, then with submerged arc welding, 30% of the composition of that will actually be the base metal that you're welding it onto. Okay, so depending upon the chemistry of your overlay, then with a single layer, it may not achieve the chemistry that you need, that's in your specification. So the big difference with electroslag welding, and this is by virtue of the way that the filler metal's melted and the surface of the base metal is melted with the electroslag, electrically heated slag. Its dilution is half that of submerged arc welding. So with taking dilution into account, then really you need, in order to achieve the chemistry, you could possibly need at least 2 layers. Okay, so you've got a 30% with submerged arc welding, you've got a 30% mixture of the base metal in your deposition. So you need to weld on top of that, and then you'll get a 30% mixture of that combined composition into the top layer, the filler metal layer. So it's a fairly easy calculation to work out, but you need to make sure that it's compensated for. The other alternative would be to use an overalloyed filler. So just like you would use an overalloyed filler metal for a joint, then you can do exactly the same, and there are grades available that are over matching. So you're trying to achieve a 316 overlay, 19 chrome, 12 nickel. So start off with something that's higher than 19 and 12. Okay, and another alternative would be to use a compensating flux, which generally we don't do. This means you're actually putting elements, you put in chromium, nickels, whatever, in the flux. So the mixture, the melting that you get there, you're actually putting alloying into the weld metal with the flux. But it's all to compensate for this thing called dilution. So in terms of the advantages of electroslag over submerged arc, lower dilution, we take that as read. Okay, it's a lower dilution. It's speed. You can increase the speed from 120 up to 180. That's the fairly standard speed, going up to 180 millimeters a minute. And with high-speed fluxes, these fluxes that we're calling high-speed fluxes, so they've been developed, designed to enable all the properties to be achieved at very high speed. So we're talking 400 millimeters per minute. So in terms of the area, the coverage is increased by anything up to 80%. Okay. The surface of the bead is better, again, by nature of the electroslag melting. The actual surface, there are less ripples basically in the surface. It's a smoother surface using that kind of process. Even though you're using very much higher amperage, the actual heat input, the heat input equation calculates be the same or even less, because you're putting more amps in, but you're going very much faster. So obviously you end up with a heat input that's relatively the same. If you've got less dilution, then it's possible to get the chemistry that you're looking for in a single layer instead of having to put 2 or more on top. Because of the electroslag heating, electroslag refining, Basically the metal is refined by being melted through and by the molten flux. And one big thing, if you're doing something where you need 100 tons of filler metal of overlay, the flux consumption of electroslag welding is at least 30% lower. So it doesn't matter if you're only buying 20 kilos, but if you're buying 100 tons, then it would make a big difference. So this is a nice table that illustrates a lot of things, really. We've got a table of submerged arc welding, basic electroslag welding, basic normal speed, and then we've got two others. One we call a medium speed and one with a high speed. So for all of these figures are for a strip that's 60 millimeters wide. So with the submerged arc, you can see we're using a current of 750 amps. Travel speed 10 centimeters a minute. You can see the heat input's 11.7. However, in order to achieve the chemistry of 347, we need to put two layers down. So we've put a buffer layer on there. We put a buttering layer, buffer layer. The first layer is a 309L. Okay, so that's a big thing. So obviously, whatever time this takes, it needs to be doubled in reality to achieve what you're trying to look for. And the deposition you get in there is 14 kilos. So with basic level electroslag welding, very similar to what you saw in the video, this is going at 1250. Sorry, the amps are 1250, but it's running at 18 centimeters a minute. So from 10 to 18 is a big step. You see the heat input is relatively the same. It's a bit smaller, but it's relatively the same. So that's not too scary. But the deposition rate shot up from 14 to 22 kilos an hour. And you see the flux consumption has gone down as well. So if we skip this one and go over to the high speed, then the speed that we're talking about is 40 centimeters a minute. So it's 4 times the speed of this. And if you remember, to achieve the chemistry, you needed 2 layers of this. So in reality, it's half of this. So from that over to the high speed, so we've got the right selected strip with a high speed flux. And we can travel at 400 millimeters a minute. Huge difference. But you see the heat inputs has gone up to 2100 amps. But as I mentioned, because the speed's increased, the amperage, sorry, has gone up to, the power has gone up to 2100 amps, but the heat input's actually lower in reality because of the heat input equation. And the deposition rate that we can achieve, there you see, is 51 kilograms an hour. It's a huge figure, absolute huge figure. And this one I just wanted to highlight because it's a unique grade. So we've got a strip that's 2311 LMB, so it's 23 chrome, 11 nickel with niobium, and we're trying to achieve a 309 LMB deposit. So here we've got somewhere in between the medium and the high speed, and basically as a requirement you need 1600 amps. So if you've got a 2000 amp machine or power source, then this is achievable, whereas this one is a little bit out of your range. We can still move at 24 centimeters a minute, 240 millimeters a minute. So it's a big step up from the basic level, and the deposition rate again has shot up to 32 kilograms an hour. So this is it's a fairly unique grade. It is a unique grade, I should say, and the ability to go with possibly more standard machinery, more standard power sources is a big advantage. Just an illustration of nickel chrome moly 3, so alloy 625. We've got composition according to AWS, and the composition of the strip of the ESAB strip. And you see with a double layer, the chemistry that you achieve, the big thing to notice really is probably the iron content. Obviously the iron increases considerably due to dilution. So it just gives you an idea of the of what happens because of dilution. So bear in mind again, this is 2 layers. So you put in this strip onto another layer of a diluted version of this strip. So this is the chemistries that you can achieve with that. You see the chrome drops, the nickel drops, moly drops, niobium drops, and the iron very much increases. A customer example of trying to achieve a 347 overlay. The requirement specification, well, this is a real example. The customer wanted a 347 overlay. It was a requirement that the ferrite content had to be between 3 and 8. Post-weld heat treatment, 690 to 715, 10 to 30 hours. It had to pass bend test, intergranular corrosion, Strauss. Had a hardness requirement, and it had to pass liquid penetrant, ultrasonic and desponding tests. So these are the actual parameters that we used. The strip was this Exciton 2111 LMB. If you may be aware that the 347 needs to be 19.9 LMB. So the strip 2111 LMB with dilution allows that to happen. Okay, so 1250 amps. Traveling at 190 millimeters per minute using the Exciton flux, and what a surprise! Yeah, it absolutely passed. So the chemistry was correct, as was the ferrite content. The post-weld heat treatment was fine, and it passed the bend test, the Strauss test, hardness, liquid pen, ultrasonic, and despondent. So they're real figures from a real customer specification. In terms of available grades, as with all the metals from us, we use this microelement control. I mentioned this with all our filler metals really. Microelements are, as the name describes, they're very tiny amounts of various metals, elements that have a significant effects on the property of the weld. Talking about strip electrodes particularly, they're developed specifically to improve the surface finish. We want the surface finish of the strip to be as flat as possible. This helps by increasing the fluidity of the weld pool and deposition rate, obviously. So these are micro elements. They wouldn't appear in your certificate, in your 3.1 certificate, because the content is so small. They wouldn't appear on they wouldn't appear on your certificate because of the content is so small, and it's really the secret chemistry, if you like. It's what we do to enable to provide a better product, if you like. So in terms of the availability, then we've got a fairly extensive range, and when you combine that with the flux, the range of fluxes, whether you want to go normal speed, medium speed, high speed, there's a number of places to look at, and there's far too many to list in a presentation like this. The website is a good point of call, as is the Exciton app, and we do have a strip welding handbook. I just want to show you that this is typically what a 30mm strip would look like. 25 kilo coil. We have 25 kilo drums, tins of the flux, and then we've got the bulk properties as well. So depending on the size of the job. This strip cladding handbook has got an enormous amount of information in it in terms of detailing of the processes, some of the diagrams that I've used in my presentation today, and it does list fairly extensively all the grades of strip and flux that we have, along with some suggested parameters, as well as some of the available equipment that we have. As with any printed material, it's out of date, so I would ask you to check the website, or please contact us for any if you have a specific inquiry about this kind of product. In terms of applications, then I don't want to get too deep in this. Time's just about up. Any big vessel like this that's operating in a corrosive environment then is absolute fair game for strip overlay. And I just want to pop this one in. It's obviously a valve, a ball valve. That strip overlay is not just restricted to flat objects. If you can manipulate the workpiece to be in the horizontal position, then you can put strip overlay on it. It's not something that you can weld at an angle. It has to be in the horizontal position. So we've seen this picture before, and that's fairly common. Provided you've got a column and boom that can reach, then you can get in there with a strip. So in an oil refinery, yeah, there's any number of vessels that would be that are lined using strip overlay, as with any kind of acid process or heat exchanger plates, or the inside of a heat exchanger tube. Again, all absolute prime candidates for strip cladding. If you were doing these with wire, then it would take you 5, 6, 7, 8, 10 times as long. So thank you for that. We'll take any questions. Clemente.
Thank you, Peter. Well received, and as well, thank you all of you for your participation and the good questions highlighted that we got in. So I will start with the first question, and that's except for corrosion protection, what else can strip surfacing be for?
I can take that, Clemente.
Yes, please. Go ahead. Okay.
Well, except for corrosion protection, for example, worn out material. It could be for example, in a digester, a batch digester, in the cone, bottom cone, for example, where you have a lot of both corrosion, erosion, eroded material. There you can put it on. Just give you an example. You can take out the ball from the ball valve again and do a strip overlay, for example.
All right, thank you very much. I go to the second one. And what is the smallest plate thickness in electroslag welding cladding? Maybe Paolo?
Yes, thank you, Clemente. It depends, of course, a bit on the welding process, if it's going to be sub-arc, electroslag, and the strip width going to be used, but in general, it has to be above 30 or 40 millimeters, because the heat input will distort the base material.
Absolutely. The size and the energy is making a big effect on that regards.
Yes.
Okay, good. Then we have a next one, and that's, would you need a longer run-in, run-out plate for starting and ending the electroslag welding process in contrast versus submerged welding?
Paolo, go on.
Yes, sorry. I am mute. It took a while to unmute, sorry. No, usually you don't need, because you can start cladding and stop the activity on the same object that needs to be cladded. Maybe you might need to go for some light grinding, but then there is no need for run-out plates, run-in and run-out plates.
Right.
Yeah, and I would say also that the electroslag process and the submerged welding, it's in principle where you start quite the same for what we have seen and processed.
Yeah, I agree with that completely.
All right, good. So, guys, the next question, a very interesting question. How many times can I recycle the used flux? Peter, you mentioned that on your presentation when you showed the movie and said that the flux can be recycled. So, what is the range or how much can we recycle on the?
No, I'll let Paolo answer this. He's the expert on this.
Thank you, Peter. Usually we suggest to add at least 1/3 of a new flux during the recycling, because of course some part of the flux on the weld pool will become slag, so it has to be scrapped. And then of course keeping recycling it will also deteriorate the grain size and the chemical properties of the flux. So at least 1/3 has to be added.
All right. Thank you very much, Paolo. And then I come at the moment to the last question. And then it's said here in the question box, which criteria to follow when deciding if submerged welding or electroslag welding should be used. So what is the decision maker to use one process versus the other one? Peter or Paolo?
No, Paolo, come on, Paolo.
Okay, I don't mind, Peter, of course. Well, this maybe it's the topic for the next webinar, because it might take several minutes, because there are many topics to consider. But at least the main ones are the technical specifications, because sometimes the end user is imposing the welding process to use. Then, of course, it can be also the know-how and the previous experience from the manufacturer, the welding equipment available to the manufacturer, because, of course, as we saw during the presentation, ELECTROSLAG is needing higher amperes. It means that bigger power sources needs to be connected to the welding torch. So, of course, maybe it depends, of course, on the scope of the job and so on, because maybe it's worth to using the current equipment and taking a few more hours than making an investment and buying more power sources. And then, of course, the total cost. As Peter explained at the beginning, everything is always about costs now, labor cost, investment, and so on.
All right. Thank you, Paolo. Thank you. The next question is, would the temperature of the weld pool be lower in relation to submerged welding, in contrast to submerged welding? And would this be beneficial for shrinkage deformation? Is that clear for you?
Paolo?
Yeah.
Peroca?
Yeah.
I'm avoiding these.
Yeah, it's a clear question, but I've never encountered it before. I mean, you have a weld pool, you have the melting temperature for the grade, and that's it. For
I think it's
some,
related to heat input, isn't it? Yes, you're putting more amps into electroslag welding, but the actual heat input is the same or less for submerged arc welding. So sorry,
yes.
Yeah, and you also have a less mix up with the base material for electroslag welding.
Yeah.
But I would also add that if we assume that the heat input is the same for subarc and electroslag, just an assumption, considering that by using subarc, less hours will be needed to have the job done, then at the end we will be adding less energy into the plates or into the shells. So probably the distortion should be lower with the electroslag.
Yes, indeed. Yeah.
Yes, I agree.
I would add also something else. I mean, first of all, it is clear that it should be brought in relation how much energy you bring in. So that means that maybe to do the overlay with a 30 millimeter than as a 60, go with a smaller size of the strip, and then to consider as well if in regards of the dilution, I can only do a single layer with electroslag welding and not a double layer in submerged welding. So that means that I reduce extremely the work and the heat that I bring into the material.
Yes.
Exactly.
Yeah.
Good questions. Hey, thank you very
much
for that. Absolutely. I don't see any more questions coming in here. So please note down, Peter, my contact, which you see on the screen, as well Paolo's and Peroca. We are already now very happy to answer further questions. With that said, we wish you a successful rest of the day. Happy Christmas, a new start, a very good start in the new year, and see you soon in the next live event in 2 months. Thank you very much.
Thank you.
Thank you all. Bye-bye.